Dear students, let's proceed with our lecture on the topic of considering schematics with so-called distributed parameters. And I would like to remind you slightly about, from the very beginning, we consider that raise high frequency electromagnetic fields is applied to schematic which dimensions is less than length of electromagnetic wave of the applied electromagnetic fields. And in such a case, we present such a schematic as totality of infinitesimal elements, and we write down first and second Kirchhoff's law, and with the help of such of this writing, we've got the so-called telegraph equations. You should remember them by heart. And then we have been considered application of sinusoidal steady-state electromagnetic fields, and in such a case we have used complex variable and phasors of the considered currents and voltage drops. And it permits us to simplify this telegraph equation and to replace derivative by time or from time by just multiplication by j omega. And so we've got and then we differentiate first telegraph equation by x by coordinate, and we substitute instead of di by dx, we substitute x expression from the telegraph equations, and in such a way we've got expression for we've got equation with only u, with only voltage drop, and we write down solution of this equation as sum of two exponents with different signs of these exponents. So in such a way we've got u, and we are supposed also to get I current, and we do it in such a way we have from the first telegraph equation we express current I as du by dx over this this coefficient R0 plus j omega L0. It is here. Then we should differentiate u to get du by dx, and it is done here, and by rearrangement and substitution gamma as square root from R0 plus j omega L0 multiplied by G0 plus j omega C0, we've got equation for current in such a way, yes? So we have this coefficient we arrange in such a way, and this expression in brackets is the same as was for voltage drop. Let's introduce variables such as ZC, its characteristic impedance of the long line. Gamma is, which we introduce in such a way, is called propagation coefficient, and it is complex number, and its real part alpha is called attenuation coefficient, and its imaginary part beta is called phase coefficient. Let's consider how we do it. We designate this coefficient as characteristic impedance, just equate it to this coefficient, and gamma, which was designated in such a way, is presented as sum of real and j imaginary part. And this characteristic impedance and propagation coefficient are called secondary parameters. Then let's consider to determine this unknown integration constant conditions either at the beginning of the line u1 or at the u1 and i1, or at the end of the line u2 and i2 should be used. Let's use here u2 and i2. Let's consider that they are known. And so we can write down that if u2 is known, if load impedance z2, impedance of the load which is connected at the end of this line is known, we can write down that I2 equal to U2 over Z2. So both these I2 and U2 are considered as known. And as we considered that x equal to length of the considered infinitesimal elements from the end of the line, it is x, when we should write down that when x equal to 0, u will be equal to u2 and I will be equal to I2. Let's substitute these 0 values in expression for u and I. When x equal to 0, we will have here u equal to a1 plus a2. Okay? As considered current, we can write down that at x equal to 0, we will have I equal to I1 over Z0 minus I2 over Z0, or I multiplied by Z characteristic, I2 multiplied by Z characteristic equal to A1 minus A2. So we have two equations with two unknown A1 and A2, and we can determine this integration constant easily. At first, we should sum up both right hand part side of this equation and left hand side, and as such a2 will vanish, and we will have that 2a1 equal to u2 plus zs I2, or I1 equal to 1/2 of U1 plus ZS I2. And when we destruct second equation from the first, we will have that A2 equal to U2 minus ZC I2 over 2. So we can write down both voltage drop and current through this integration constant, substituting here known U2 and I2, current and voltage at the end of this transmission line. So we write down that U from here equal to, instead of A1 we write down that it will be U2 plus ZC I2 1/2, this 1/2 multiplied by E in the gamma X, plus 1/2 also, and then I2 U2 minus ZC I2 multiplied by E in 3 minus gamma X. The same refers to I, current. It will be the same, but here will be minus instead of this plus, and here will be I1 over ZC. So if we change places of these two summas, we will have here for the second summand. For the first, it will be I1 A1. It's I2 over I2 ZC over ZC. It will be just I2. And second summand will be U2 over ZC, and it should be multiplied by E in the degree gamma X. Next, we will change places of these two summands. It will be, and write down not minus here, but plus. It will be 1/2, and it will be, for this item, it will be ZC I2 over ZC, it will be just I2, and here it will be minus because we change change places and write here not minus like here, but plus, and it will be ZC I2 over ZC just I2 multiplied by inserting minus gamma x. So we've got this expression both for voltage drop and current across this line, independence of location of infinitesimal element relatively the end of the line, this x. See, x is distance, x is distance between the considered infinitesimal element and the end of the line. You see here we may use hyperbolic functions. Let's introduce here hyperbolic sinus, cosine, and hyperbolic sine. Let's proceed. We will not be in time to fit permitted length of YouTube lecture. So let's do it in the next lecture. And now, please, I would like to remind you that now we consider this long line and we write down the so-called telegraph equation, then we transact to presentation to considering steady state AC processes. We've used here phasors, and with the help of replacement of derivative by time by product of corresponding volume and j omega, we've got solution for voltages and currents through the so-called secondary parameters. Bye for now. Let's meet in the next lecture, and I will explain you how it may be used. Such approach can be used to determine voltages and currents, and to determine how what parameters of the lines are necessary to transact signals without distortion. Bye for now.